So we're going to continue looking at limits, and again we want to highlight a few things in that when we divide by 0, okay, we have to be careful from which side of 0 we're dividing by, because as we divide from the positive side, our limit is going to be positive infinity, and as we divide from the negative side, it's going to be negative infinity. So if I draw a picture of this, 1 over x is going to go up like this, okay, from the positive side. Okay, so that's going to be positive infinity. So that's going to be what's going on here. And as I approach 0 from the negative side, okay, it's going to look like that. And from the negative side, it's going down to negative infinity. Okay, so we have to be careful which side we're approaching 0 from. The 0 divided by 0, okay, this is the problem with limits, or this is the problem that allows limits to deal with, is this can be anything. Same with infinity over infinity. It can be anything. It could be 0, it could be infinity, it could be 15, it could be pi. We don't know. Okay, and really this 0 times infinity is just a kind of a hidden form of 0 over 0. And with limits, what we're going to do is compare the ratio of the numerator to the denominator. Okay, and that's the best way and most effective way we're going to deal with ratios, in the most common way as well. So we're going to characterize these limits into two types: endpoint behavior, so what's happening at infinity, okay, and what's happening locally as x approaches some values. Okay, so these are local behavior ones where we're looking at x's going towards some local point. Okay, so as x approaches, in this case, -3, or we're going to look at x approaches +3. So as x approaches +3 from the positive side, right, we have these left and right hand limits, and these tell us different things. So as we approach from the positive side, this is a one-sided limit. It allows us to evaluate these points which are discontinuous. Okay, so here, there's my limit from the positive side. It's going to that point there. And it looks like it's going to -3. Okay, so that's my right-hand limit. From the left-hand side, it looks different. Okay, so we need to have a different limit coming from the left. Okay, so we need to do these as one-sided limits. Okay, as a two-sided limit, this limit does not exist, but from the right side, it's equal to -3, and from the left side, it's equal to +2. Okay, so these can be evaluated as right side and left sided limits. And again, just a reminder, limits are where it looks like it's going. Limits don't care that this actually ends up at -1. Okay, the fact that it ends up at -1 here, that's irrelevant for limits. Limits don't really care. In fact, limits aren't useful for evaluating what's happening at that point. Limits are used to go to points that we can't get to. Okay, and we need a limit to do that because we want to see where it's going. So because the limits are not the same from left and right hand side, we start talking about this issue of discontinuity. Okay, and discontinuity is exactly what it looks like. It breaks apart. Okay, so when we talk about discontinuity, we're going to have formal ways to deal with this, but in the end, your eyes don't lie. If it breaks apart, it's discontinuous. Okay, and we also say that no limit exists at 3 because the left and right hand limits don't match. Okay, so unless the left and right hand limits match, we can't say that we have a limit. Okay, or in this case, this would be a two-sided limit right there. Okay, so let's take a look at another point at x equals 2, or as x goes to -3. Okay, -3 from the positive side. Okay, it's going to look like this. It's approaching -3 from the positive side. And yeah, it looks like we have a y value of 2. As we approach it from the negative side, okay, so -3 from the negative side, it looks like it's approaching the same point, okay, which is 2 as well. And since the left hand and right hand limits are the same, we say that the limit is equal to 2 from both sides. So this is a two-sided limit. Okay, so this is a two-sided limit, and this two-sided limit exists. And unless the limit matches from left and right hand sides, the two-sided limits do not exist. Okay, so there's lots of issues that are starting to show up here. Okay, we have this issue of left and right hand limits and two-sided limits. We have this issue now of, I've introduced a discontinuity. In discontinuity, although we're going to have formal ways to define it, we want to make sure that we understand what a discontinuity is. Visually, if it breaks apart, okay, your eyes don't lie. Okay, so graphs are the best way of understanding limits. Okay, if we can look at something and we can say that a limit exists, we can see it. We can actually see it. So, but we want to also have some formality to this. Okay, some limit formality. And the following criteria is what we're going to use then. So this is what we just talked about a little bit earlier, that the left-hand limit and the right-hand limit, sorry, this is a right-hand limit and left-hand limit. If they are the same, okay, and they're equal, then we say that a limit exists. Okay, that was the issue right here. The left-hand limit and right-hand limit are the same, so then we say that the two-sided limit exists. If the left-hand limit and right-hand limits are not the same, we say the limit does not exist, or D and E. And that was the case here. Okay, we have the left-hand limit and the right-hand limits. Okay, they are different here and here. So we say that the limit does not exist. Okay, so the two-sided limit doesn't exist unless the right-hand and left-hand limits match. So let's state if the limit exists. Okay, we're approaching -4 from the positive side. So -4 from the positive side looks like this. Okay, so it looks like it's going down like this. Okay, so it looks like it exists at -infinity. Okay, and again, there are some books that say that because it's -infinity, it doesn't exist. But typically, we would say that this is going to a limit of -infinity. What about -2? Okay, and this is a positive, the one-sided limit, so that's okay because there's nothing on the other side. So if this was a two-sided limit, it wouldn't exist. What about as we approach -2? We're approaching -2 here. Actually, I should use a different color. We're approaching -2 here. Looks like it's approaching 2. And from the other side, it looks like it's something different. Okay, so because the two limits are pointing in different directions and to different places, we have to say as a two-sided limit, it does not exist. At x equals 0, okay, we can say that it's going to this point. Okay, in fact, it's continuous because there's a point there. So continuity has something to do with these limits existing. So as x goes to 0, it equals 1. Okay, now just because the limit exists doesn't mean it's continuous, because it could still be a hole. But if it equals 1 and the point exists at the limit, then we can say that it's continuous because we don't have to lift our pen to draw through that point. So this case is actually continuous. Okay, but again, the limits don't care what's happening at that point. It's just worried about what's happening as we get to that point. So this is the same issue here, except this is slightly different. So this is the same limit. The limits are exactly the same as going to 0. So left and right hand limits, okay, they're the same, just like we had up here. The left hand, right hand limits are exactly the same. So from the limit perspective, these are exactly the same question. Okay, it's equal to 0. The difference is this is discontinuous. So just because there's a limit, just both of these have a limit, this was continuous, this was discontinuous because there's a hole in there. Okay, there's a jump. Okay, so it's a jump discontinuity. So because of that, we can't say it's continuous. However, from the limit perspective, we do not differentiate between these two. Okay, because the limit, again, does not care what's happening at that point. So looking at these algebraic limits then, how do we deal with these? Well, if I talk about the limit going to this square root function, okay, 1.5 or 3 over 2 is going to give me 0. The problem is, this implies that I'm approaching that coordinate from both sides. Okay, and the square root function, I'll just sketch it over here. Where's the place I can sketch? I'm going to sketch it over here. This square root function is going to be, there's our 3 over 2. It's not defined on this side of square root of 3 over 2. So this limit cannot exist, okay? Because as a two-sided limit, it cannot exist. However, as a one-sided limit, okay, this does exist. And exists and is pointing towards y equals 0. Okay, so this again is the issue of one-sided versus two-sided limit. This doesn't exist as a two-sided limit, but it does exist as a one-sided limit. So this log x function, as we approach 0, okay, again, this is a problem because a log function, if we take a look at a log function, this is log x, it's only defined from one side of 0. So this implies that you're approaching 0 from both sides. Okay, so it does not exist. As log x approaches infinity, okay, this is easier because infinity by its nature is a one-sided limit, and although log x grows very slowly, it will eventually get to infinity. This last one here, it's not the last one, but the last one for this page, we have this function. Okay, I'm going to draw it here. This is going to be 2 over e to the x. It's actually an exponential decay graph. Okay, but what's happening as we approach 0? Okay, well, we actually have no problem because as we approach 0, it actually is, we can actually evaluate this value at 0. So this becomes our two-sided limit from this side and this side. There's no hole there, so we just plug it in. We go 2 over e to the 0, well, that's equal to 2. Okay, so make sure that when we have limit notation, that if we can actually evaluate the limit, we actually just plug in and evaluate. It doesn't have to be, some limits aren't used for these, difficult places. Sometimes they're just used to evaluate some points. Okay, but again, it doesn't tell us, the limit doesn't tell us exactly what's happening there, but we could use that point there to evaluate the limit.